first thing to discuss today is the schedule you picked up on the way in. So we are entering Unit 4. Unit 4 is on enthalpy, which is kind of the heat involved within chemical processes, and equilibrium. Again, both these topics we touched upon a little bit in Chem 1. Definitely have to go more in depth here in AP. But if you look at our schedule, again, we have class Tuesday and Thursday of next week. Basically, each class period, I'm covering a new kind of concept and calculation for enthalpy. That's how I have this all arranged. Now, I can't say I know 100% certain what's happening during finals week because I haven't been told. Staff is kind of in the dark like students are. The early draft that I saw shows that you guys, being first hour, are probably going to have class on January 18th in the morning. I think there's going to be like an extended contact time to start off the day, so we're not going to be meeting at 8:15 necessarily. We're probably meeting at something like 10 o'clock or 9:30, something like that. Boy, my hope is on Monday during homeroom, everyone now knows what's going on during finals week. But we are not taking a final during that week. Instead, we're going to learn another thing on that day. We will do a little lab activity as well. I actually misspoke. I believe I told you guys last time we're doing an actual lab. Now I'm saving that actual lab for the beginning of second semester instead. So the schedule I gave you is for this entire unit, which means it's the beginning or the end of this semester, beginning of next semester. So finals week, we don't have a final. Instead, we just have normal class. And then we start second semester, and we're just going to actually do a practice test on that day to see where we're at the moment. And then we continue back into stuff. So day 2 of second semester, we have a lab. Day 3 of second semester, we're going to have a quiz on enthalpy before we move into equilibrium. So there's the schedule. And now we can get rolling with what we have to do today. So what I'm trying to do with your packet from now on, and there's no warm-up today because we're starting a new unit. Whatever notes you want to take in your notebook or whatever is fine. Anytime there's a calculation, I already put that into your packet, like the practice problem wording. So if you are someone that takes notes, you can have it on your notebook, but then you can also have like page 2 of your packet open. Because then, when we eventually get to math, you don't have to rewrite the entire practice problem. Saves you a little bit of time and energy, it saves me a little bit of time. Enthalpy is all about energy. Now, enthalpy is going to be typically focused on heat, thermal energy. But this first slide is just a reminder of different types of energy. Again, kinetic energy is energy of motion that's related to the temperature of things. We talked about that with gases and how temperature is a measure of the average kinetic energy. We really don't do much about potential energy when it comes to the position of objects. That's much more of a physics topic. But chemical energy, sure, we do a lot of that. So my first reminder is just a little bit about energy. What is energy? What are some different forms of energy? We're going to focus on the heat created by and large. Heat is something that transfers. My picture on the bottom left corner. You have a hot object and a cold object. Heat will transfer from the hot object to the cold object. But energy in general, as the heading of this slide says, is that ability to do work, that capacity to do work. My next slide is a little wordy, but really it's my last slide of content before I just go over a couple of math problems. So notes should be hopefully pretty quick today. On the left-hand side are terminologies that you should be comfortable using now that we're entering our kind of thermal chemistry, our enthalpy portion of the year. Whenever we are doing an investigation that involves a change in temperature, one thing's gaining heat, one thing's losing heat. Energy is transferred, not created or destroyed. That's your first law of thermodynamics. We need to be able to, when we look at any process that's involving a change in temperature, a change in heat, we need to be able to identify what is the system, which is the focal point of our study, versus what is the surroundings, everything else. Because depending upon your point of view, it makes a difference of what's actually happening. The terms endothermic and exothermic. Hopefully we're comfortable with those because we looked at those with the energy profile diagrams, you know, your activation energy curves. So recognizing if something is endothermic, it is gaining heat. Heat is going in. Endo, in. Thermic, heat. Heat is coming into the system. Well, where did that heat come from? It came from the surroundings somehow. Again, we're about 13 minutes away from me cracking open a nice cold Mountain Dew. Unfortunately, as I let that Mountain Dew sit in this room, even though this room is kind of cold today, it's going to warm up. It's going to be endothermic. It's going to take in heat from the surroundings, this room. Is that a cold drink that you have there? I mean, it looks coffee, so I didn't know if it was hot or not. But if you had a hot coffee brought in over time, the hot coffee would cool down. It would lose heat to the surroundings. It would be exothermic. Exo, exit, meaning to leave. So again, on the left-hand side is common vocabulary we need to be comfortable with. Heck, I believe in your lab report at the beginning of second semester that's on enthalpy, you're going to be using these terms to describe what happened when you do two different chemical processes, a dissolving and then a chemical reaction. On the right-hand side, a reminder, joules is our unit of energy. Again, calories is the American unit of energy. Joules is the international unit. Most commonly, you're going to see kilojoules, so that metric conversion as well. There's 1,000 joules in 1 kilojoule. Kilojoules per mole is very common for our unit of energy, because now it's not just the amount of energy, it's per mole of a substance. Because obviously, if you have more of something in a chemical reaction, it should produce more heat or take in more heat, depending on if it's endo or exothermic. Speaking of endo and exothermic, a lot of math. Again, like I said when I introduced the schedule, every day we're going to cover a little bit of math in this class, a little bit of new math each time. Numerically, when you solve for your enthalpy, when you solve for your heat, if it's a negative value, that means it's exothermic. That means heat is leaving the system to the surroundings. Negative is exiting. This is the beginning of our thermodynamics that we have to do in AP chemistry, but the very last unit we do before we do practice tests is going to be also on thermodynamics. And the idea of a negative being system losing and a positive meaning system gaining, you're going to see that come up again in hopefully late March is when we get to that last stuff, so we can get out April to do practice tests. So a positive answer for your heat calculations means it's going to be endothermic. And then you can just see I have an example on that right-hand side. You know, system gains 150, surroundings lose 150, conservation of energy. We could just use that with numerical values. To give you practice with system, surroundings, endothermic, exothermic, I just have two kind of sample problems on the bottom here. NH3 is ammonia. Very common weak base that we will talk about second semester in our acid-base unit. The process that I'm showing in this first bullet point is ammonia going from a gas to a liquid. So it's going a phase change, a physical change. This is going to be condensation. When you go from a gas, you condense it into a liquid. If I were to label whether or not this is endo or exothermic, I would just have to think to myself, when a gas transfers into a liquid, does it need to bring in heat or does it need to release heat? And hopefully we can recognize that the gas needs to lose heat in order to go to a liquid. So this process here would be labeled as exothermic. Now the second one, this is one where we really have to keep in mind the idea of system versus surroundings. When you go outside and you grab a handful of snow, your hand is going to feel cold. If your hand feels cold, your hand is losing heat. So if our system is your hand losing heat means it's exothermic in terms of your hand. But what if the snowball was our system? The snowball would be gaining heat from your hand. That's why things feel cold. You lose heat, because heat always transfers kind of downhill. Something hot, something cold, there's going to be a balance. If the snowball was our system, it would be gaining heat and it would be endothermic instead. So one of the things I ask of you is to kind of keep that idea of system versus surroundings in mind. It could be in general questions like this. It's also going to pop up in our calculations when we start doing positive and negative values in a little bit as well. And then the last statement I have on the bottom of the slide, remember, why do things get cold? It's not because you can zap things with cold. Heat is the only thing that can transfer. Again, if you have a cooler full of ice and you put warm soda in it, eventually the soda will become cold. Not because the ice is cooling the soda. The warm soda is losing its heat to the ice. I mean, that's why the ice eventually melts then, as it's losing its heat. Don't know if there's anything you really need to jot down in here, but I just wanted to remind you, again, this first graph is endothermic. Again, you have to put in energy for every reaction. Every reaction gives off energy, but there's a net input of energy in this first one. The second graph here is exothermic. Again, every reaction has an input of energy and an output of energy. This one, there's more output, so the net output is the delta H, the enthalpy for that particular process. So I just wanted to remind you of something that we've seen already with endo and exothermic. All right, here we go, math time. Q equals mc delta T is the very first equation in the thermodynamics / electronegativity section on your equation sheet. So you do not have to memorize this equation. And again, like the equations on the equation sheet, what they do then is they tell you what the variables mean. Q stands for heat. When we solve that, that will be in joules. C stands for the specific heat capacity. Now, for water, you should know this value. Unfortunately, you are not given 4.184 joules per gram degree Celsius. That is the specific heat capacity of water. In Chem 1, when we went over this same type of calculation and work with you, one of the things we like to bring up is the heat capacity of water is pretty dang high. What heat capacity means is how much energy do you absorb before your temperature changes. Water requires a lot of heat in order to get its temperature to change. And if you think about Every year, for example, when I go and take the family camping, it's cool to camp at Lake Michigan and bring the kids out to the beach there where there's, for Wisconsin, we're not talking, ocean-wise. There's decent waves for them just to kind of run into. If you've ever gone camping and then swimming in Lake Michigan in late June, I don't care if it's a 90-degree day, it sucks. I mean, we did that one year. The sand was too hot because the sun's beating down, it's 90 degrees. Okay, I'll go in the water. The water is not warm. You're starting to cramp up really bad because of how cold it is. So now you have to make the decision of what am I going to do? I'm sorry for anyone who has stock in campgrounds on Lake Michigan. Don't go there in June. But this year, I'm going to be going in August. Big bodies of water need a lot of time to warm up. But if you can go in August at some point, it's pretty nice going out on Lake Michigan at that point. And it doesn't have to be a 90-degree day anymore. It can be a 70-degree day, but the water has absorbed a certain amount of heat at that point. On the other hand, you take things like metals. Metals are easy to heat up and cool down. Again, one of the things we've had Chem 1 students do is if you held something metal like the desk leg, it feels really cold compared to your desktop. Metals have really low heat capacities, meaning that they absorb heat really quickly from you. That's why it feels cold. Your desktop and your desk leg are the exact same temperature. They're in the same room. It's not like I disassembled them and heated up one, assembled them really quickly, and then you came in, ha ha ha, I got you guys good. No. It's all the same temperature, but they feel different based upon that heat capacity. We will do little lab activity next class period with heat capacity. So you'll kind of see the difference in heat capacity between things. But water's value, one that hopefully you have written down, one that you will know, because it's not typically given to you. Finally, the triangle means change. So this is delta, it's the Greek letter delta. Delta T is the change in temperature. Final temperature minus the initial temperature. This is really the only new equation that I'm giving you today. I'm just going to show you 3 different ways now of how to solve it, and then that's going to be our day where you can then do some practice problems. Quite frankly, we'll probably be done a little bit early today as well, but within thermodynamics, I just want to take one chunk each day. I don't want to overdo it here where we lose what we're trying to get. So again, so I can kind of write things down, I'm just going to switch this over to here. The question that we're going to solve, which again is on your handout, says a 50-gram sample of water is at 22.5 degrees Celsius. And its temperature increased to 37.4 degrees Celsius. How much heat did it gain? And this is as basic of a Q equals MC delta T problem that I can give you. The mass is 50.0 grams. C is the specific heat capacity. Again, how well a substance absorbs heat. Every substance varies with that. The C value for water is 4.184. The unit for heat capacity. Unlike the rate constant K's unit, 1 over molarity seconds, 1 over molarity squared seconds, depending upon what order of reaction it is. I've told you before, like the rate law constant K, or the ideal gas law constant R, 0.08206 liters atmospheres per mole Kelvin. Those units are only there to cancel things out. They actually have no meaning. This kind of has a meaning. How much energy does it take to make 1 gram increase by 1 degree Celsius? Now, when you think about Lake Michigan, there's a lot more than 1 gram, so it takes a lot of heat throughout the entire spring and summer to get that temperature to raise where I'm willing to go swimming in it. I point out this unit otherwise just to remind you, when we do math in this class, a lot of the math that we do is kind of converting from one thing to another. Keep an eye on your units, because then you can recognize where do I start and where do I end. As for delta T, final temperature is 37.4 minus initial temperature, which is 22.5. Typically what I like to do is I like to write it out like that, and then, you know, kind of right up above, I just figure out what is that. Quick reminder of everyone's favorite thing, significant digits. When you add or subtract two measurements, like I just did for delta T, the rule is the place they have in common last. These both go to the tenths place. That's why this answers to the tenths place. I know some might say this has 3 digits, this has 3 digits, this has 3 digits. That's not actually how we should do it. Because just for a second, imagine if instead of 37.4, this was 27.4. 27.4 minus 22.4 would just give me 4.9. So I would have only 2 digits. The weird thing about sig digs, when you either add or subtract, you go to the place they have in common last. That means you could potentially gain or lose a digit in that process. Don't also put a 0 at the end here and call it, 4.90 in that one example. So be careful with sig digs. But now it's just multiplication. 3 digits, 4 digits, 3 digits. My final answer should have 3 digits too. And this one, if I go to 3 digits, it's going to be 3,120. My unit is a joule. If the temperature decreased instead of increased, our delta T would have been a negative value. Therefore, our Q would have been a negative value, telling us it's exothermic instead of endothermic. So make sure when you have your change in temperature that you're putting it in the correct order, final minus initial, in order to get the sign of the Q correct. Just keep on hearing this rattling going on. This something makes me think of like there's crickets in the background. You know, this class is that boring that there's crickets. By the way, on the right-hand side, when we do calorimetry, when we are going to be doing our measuring of heat change, we do the styrofoam cup calorimeters. I know Rademacher in Physics 2 has really fancy calorimeters, but AP questions are usually based upon the very simple ones. Plus, then you're always going to have a source of error that's not perfectly sealed, so heat can be exchanged between the surroundings and what's going on in the cup. But I have all that over on the left-hand side of the room, because, again, next class period, we're going to do a little lab activity with it. After that, we're just going to keep on each day doing something with that. All right, my last slide of content is 2 more practice problems. So, again, this is already on your sheet. What I'm trying to do is take the problem that we just did, but I'm going to add something to it. Because in the first question I just said, hey, the water warmed up. Well, let's go over why the water could warm up. So here's my second question. 50-gram sample of water at 22.5 degrees Celsius has its temperature increased to 37.4 degrees Celsius. When a 25.2-gram piece of metal at 95.1 degrees Celsius was placed in it, what is the heat capacity of the metal? Oh boy, let's see here. 2 years ago, if you took chemistry, I bet you did a lab where you had to solve this exact thing. Last year, I don't remember what you guys did last year. Let's try to forget last year as much as possible. But I'm pretty sure 2 years ago, you were still in person when we went over calorimetry. Sound right? Okay. Here's the key to this problem. typically, when you see anything involving calorimetry, this changes what happens to this, your best bet is to first figure out what happened with the water, the Q of water. So, my mass of water is 50.0 grams. 4.184 is my heat capacity, and I already told you the delta T last time because I'm using the exact same numbers. It's 14.9. So let's just rewrite that number that I had before. That was 3,120. Okay, so again, what this question says is, I have water, and it heated up because I put a hot piece of metal in it. I have 22.5 grams of that metal. The metal was at this temperature when I started. I want to eventually solve for the heat capacity of the metal. Whatever heat the water gained must be what the metal lost. Conservation of energy law. One thing gains, another thing loses. If the water gained 3,120 joules of heat, the metal must have lost 3,120 joules of heat. Why did the metal lose heat? It was hot. And I put it into something that wasn't as hot. Heat always transfers downhill. So this statement that I wrote in green allows me then to do my second set of math. Where what I'm going to do is I'm going to take the Q of the metal equaling MC delta T. The Q of the metal is negative 3,120 joules. Same numerical value as the water, I just flip the sign. The mass of the metal, 25.2 grams. That's given to me in the problem. I'm asked to solve for the heat capacity, so that's the variable I don't know. Let's call it C. And then finally, delta T, change in temperature. Final minus initial. When I read this problem, it says a 50-gram sample of water at 22.5 degrees Celsius has its temperature increased to 37.4. When a 25.2-gram piece of metal at 95.1 means that's the initial temperature, was placed in it. So initially, I have water at 22.5 degrees Celsius. I have metal at 95.1, and I put the metal in the water. Even though there's no mention of the metal's final temperature, it's in the problem. It's this right here. Because at some point, they're going to balance each other out. The heat gained and lost is going to balance. So this is T final. So if it's final minus initial, I'm going to write down 37.4 minus 95.1. Again, I like to typically figure that out right up above, negative 57.7. Once you're at this point, it's algebra for you guys. I need to isolate the variable, so I'm going to divide by 25.2. I'm going to divide by negative 57.7. The nice thing about having that negative sign there is that negative will cancel out with the negative of the metal, because there's no such thing as a negative heat capacity. If you get a negative C value, recognize you did something wrong algebraically. A negative C value would mean I put something hot in you and your temperature goes down instead. If you could find anything that could do that, our energy problems would be solved, because then we could take something cold and create energy after it, and that doesn't make any sense. Notice how the delta T for the metal was a greater number. The temperature change was greater for the metal than it was for the water in the previous problem. That's because water has a high heat capacity. Its temperature won't change as much. It can absorb heat really well. This calculation that we just did is what you're going to have in the laboratory next class period as a practice. It's what we did 2 years ago in Chem 1 as an actual lab. Again, I don't recall if we were able to do it last year with how we were all over the place. I have one last question. And this last one is similar to the lab activity that we are going to be doing actually on that final exam day. Another way we can change the temperature of water is not by just putting something hot in it or something cold in it. We could mix something with it. We could dissolve something in it. And that's what this question is going over, is I'm going to make a solution. My solution started at 22.5 degrees Celsius, increases to 37.4 when I add 10.6 grams of sodium carbonate. So I can take room temperature water, room temperature solid solute, put it in and mix, and my water can either increase or decrease in temperature. That's what this question is saying. So what we're going to do with that information is we are going to solve for enthalpy, delta H. The most common unit for enthalpy is kilojoules per mole. Now we want to do this for the solute. This question starts off with solution. Technically, it's not just water, because it's water and the solute in it. So because of that, I had to give you a C value for the solution as a whole. So it's a little bit better at absorbing heat when it's water and sodium carbonate versus just water. Is it 14.9? Okay. Step number one, whenever we're talking about anything experimentally that can be done with your calorimeter or your styrofoam cups, solve for the solution or the water. Q equals MC delta T. Now this is slightly different of a value. Instead of 3,120, it's 3,130 because my C value has to be adjusted for the fact that it's no longer just water that's involved in the heat absorption. It's the water sodium carbonate mixture. Next thing I would do is I recognize that that unit is in joules. I want kilojoules. .13 kilojoules. That value is the amount of heat that the solution gained. If the solution gained that amount of heat, the dissolving process or the solute within it must have lost that amount of heat. So that means my Q of solute is going to equal negative 3.13 kilojoules. One thing gains, another thing loses. This question initially was asking for the delta H in kilojoules per mole for the solute. What I've shown you so far is I could find the joules of the solution, flip the sign to make that the joules for the solutes, do a metric conversion to get that to kilojoules. I still have to get the mole part though. 10.6 grams, where are you? Right here. We can convert that into moles. That's going to be my next step. 10.6 grams of Na2CO3. I can convert that to moles using my periodic table, which is 105.99. I think I picked a mass to make the math nice and easy here. Because remember, if I use more sodium carbonate, more heat should be created. So my last step, enthalpy, which is the delta H, is the kilojoules per mole. Negative 3.13 kilojoules divided by 0.100 moles, which means I have to move the decimal place over 1. Negative 31.3. Which means, if I were to dissolve sodium carbonate in water, that's the amount of energy that would be released by the sodium carbonate. Less I use, less heat. More I use, more heat. But that is kind of the known, the enthalpy value of it. In this enthalpy portion of the unit, a lot of what we have to do laboratory-wise is using a styrofoam cup, finding out what happens to the water or the solution, and then flipping the sign, and convert to moles. You're seeing a lot of the experimental stuff right now of what we have to do. A lot of the math that I have to go over later in this unit is a little bit beyond what we do experimentally, but you still have to be aware of. So again, that was my last slide. You do have a packet with some other practice problems you can work on. We have a homework. It's been a little while since I gave you a homework. So on Schoology, you have a homework on this type of stuff as well. Again, these are the pages in the textbook that could be of assistance to you. Don't forget, again, next Wednesday, for those of you who are interested, we can do a retest as well. But the last little over 20 minutes is for you guys. Again, I could have my page with the answers for the practice problems out, if you need that. Otherwise, if you have questions, let me know. Otherwise, just your time to work.